homework solutions to the Chapter 6 homework, which had some questions and problems, and the Chapter 7 homework, which had some questions and problems. So Chapter 6 was due on Veterans Day. Chapter 7 was due on the 13th. We ended up just going over all of them on the 13th. At any rate, so question 8, an astronaut takes his bathroom scale to the moon and stands on it. Is the reading the scale his weight? It is, because that's defined as the normal force on him from the scale. And so that reading can change in different locations of the universe. The mass of the person would not change unless, for some reason, well, not in a short period of time. Anyhow, question 11 says an astronaut orbiting the Earth is handed two spheres which have identical outward appearances. One's hollow, the other's filled with lead. How could they tell them apart? So this is pretty straightforward. That idea of resistance to change is called inertia. So more mass, more inertia. You could feel that difference if you try to change their motion by shaking them back and forth. The problems for Chapter 10, the first one was problem 10, Chapter 6. First problem is problem 10. So it shows force acting on a 2 kilogram object as it moves along the x-axis. That was this graph here. And it's asking, it says the object's at rest at the origin. What are acceleration and velocity at 6 seconds? Well, at 6 seconds, this is along 0, so there is no acceleration because there's no unbalanced force. To find out how fast it's going at 6 seconds, we need to think about the acceleration during these other times. So if it's a 2 kilogram object, then 4 newtons divided by 2 kilograms gives me 2 meters per second squared for the first 3 seconds. So acceleration times time gives me 6 meters per second at the end of that time interval. From 3 to 5 seconds, we have a net force of negative 2 newtons, so an acceleration of negative 1 meter per second squared. So from 3 to 5 seconds, we lose 2 meters per second velocity. So after 5 seconds, our velocity is 4 meters per second. So the answer is a velocity of 4 meters per second and acceleration of 0 meters per second squared. There could be other ways to determine this when we study momentum, by the way. This is out of order. It's number 45, so I did that just for space constraints because I knew 40 was going to be a long question. So I'm going to go to number 40 next. Number 40 has this foot and traction, which I decided not to draw. This is a key point. So essentially what it's doing is it says that this is 6 kilograms, the boot here, the foot is 4 kilograms, and it's asking you what this angle is here so that the foot could be suspended by the ropes. In other words, and so first thing is the tension in the rope. And if it's not accelerating, the tension is going to be the same everywhere. So it's just M times G, that's 58.8 newtons. So 58.8 newtons here, 58.8 newtons here, 58.8 newtons here. The second one, part B, was asking if this traction force needs to pull straight out on the leg, what's the proper angle? So if it wants to pull straight out, essentially at this key point, the boot's weight down would be 4 kilograms times 9.8, that's 39.2 newtons. This would have a downward force also of that tension, 58.8 newtons, times the sine of 15 degrees. And that would need to be counteracted by 58.8 newtons times the sine of this angle. So this upward force, or the upward component of this tension, has to hold up both the boot and the tension going down. So basically I have force up equals force down. I know that T is 58.8 newtons. That's the force of the weight of the foot. That's the tension acting in this part of the string right here. So end up saying 58.8 sine of the angle is equal to 54.4 newtons. Do a little trigonometry. Sine is equal to 54.4 over 58.8. Inverse sine of 54.4 over 58.8 is 67.7 degrees, so around 68 degrees. So to think about the traction force, in other words, how much force is being pulled out, we have to think horizontal. So the traction force of the force pulling back to the left would equal the components of the force to the right. So I have 58.8 newtons cosine of 15 degrees. That's the horizontal component of this. And 58.8 newtons cosine of 67.7 degrees. It's the horizontal, again, component of that part. And that ends up being 79 newtons. So kind of an interesting medical problem related to the physics. Problem 45 is the next one. It says a rifle with a barrel length of 60 centimeters fires a 10-gram bullet with a horizontal speed of 400 meters per second. Strikes a block of wood and penetrates a depth of 12 centimeters. So what's the resistive force? So in this particular case, I want to think about I need to find the acceleration, and since I know the mass of the bullet, I could find out the force on the bullet. So the mass is 0.01 kilograms. The acceleration I get by using a kinematics formula. So the magnitude of acceleration is 6.67 times 10 to the 5th meters per second squared. Technically it's negative. I'm not really interested in that. I'm really interested in the magnitude of the force, or the acceleration multiplied by that mass. That gives me 6,670 newtons of average force. For part B, it's asking how long does it take the bullet to come to rest. Well, if we know our final velocity is 0, we know our initial velocity is 400, we know that the acceleration is what we determined earlier, so we can take the change in velocity 400 divided by 6.67 times 10 to the 5th meters per second squared, and that's a really short time interval. So it's 0.0006 seconds, I think, so 6 times 10 to the negative 4th seconds. Did number 40 already, and here's number 57. So problem 57 essentially has a picture of a 1 kilogram block of wood, and it's pressed up against a wall. You do need to know the coefficient of friction for wood on wood. That's in the chapter, table 6.1. I think I listed that in my quick solutions. So in this particular case, the force up is equal to the vertical component of this. That's 12 sine 30 degrees. That's 6 newtons. Force down on this is mg. That's 9.8 newtons. The normal force is basically the component of this pushing in. So that's 12 times the cosine of 30 degrees. And if the coefficient of friction we found out to be 0.5, that says the maximum static friction would be 5.2. So if the difference in vertical forces is less than 5.2, the object's going to move, and that's correct. So it will not move. Technically, the force down is greater than the force up. The force down of gravity is greater than the force up from this force. So technically, friction will be pointing upwards. But overall, the block won't move. Going to Chapter 7. Chapter 7, conceptual questions. I always thought that 10 was kind of funny. So 9 is about a tug of war. 10 is why the heck won't this accelerate? Why won't putting a magnet in front of it make it go? There are forces between the magnet and this part of the cart, but that is a whole system. So that's an internal force. It cannot propel things. You need an external force to propel things. And the reading on this spring scale, since it reads in kilograms, is 5 kilograms. It's the same as if this was just attached to a wall. So kind of neat. In terms of problems, problem 8 is the first one. So you have a 1,000 kilogram car pushing an out of gear, meaning in neutral, 2,000 kilogram truck. The wheels of the car push horizontally against the ground with 4,500 newtons. We can ignore friction. So what's the magnitude of the force of the car on the truck? First of all, I've got to get the acceleration. So acceleration of the system is net force over total mass of the system. This system is 3,000 kilograms. So 4,500 newtons of force on the ground, or from the ground, so that's 1.5 meters per second squared. Next, I want to isolate the truck. So if I want to find the force acting on the truck, now its acceleration has been defined, so the only relevant force acting on the truck to affect its motion would be the force of the car on the truck. So F net is equal to F car on truck, and that's mass of the truck times A. So therefore, 2,000 times 1.5, that's 3,000 newtons of force of car on truck. And due to Newton's third law and interactive forces, the force of truck on the car, also 3,000 newtons. The next one is going to be problem 21. Oops, sorry about that. And this is kind of like the one with the boot and traction in the last case. So it says a mobile at an art museum has a 2-kilogram object hanging here. I think it was a cat. And a 4-kilogram object hanging here was a dog. And again, just pieces of art. It's not real cats or dogs. And so you're given the fact that this angle is 20 degrees, and you're asked to figure out the tension and angle of this rope. So we've got to kind of work from this spot to this spot. At both points A and B, the forces are balanced both vertically and horizontally. So what I can do is I can look at point A, and I can say, all right, if this is 2 kilograms, I know there's a vertical force down of 19.6 newtons. That's M times G. And therefore, there has to be a vertical force up of 19.6 newtons. And that's going to be equal to this tension times the sine of 20 degrees. So that T1 comes out to 57.3 newtons. At this point, I know the horizontal forces also have to be balanced. So this tension, which I'd already found out, times the cosine of 20 degrees is the leftward force. The rightward force is tension 2. So left is T1 cosine of 20 degrees. That equals T2. That's 53.8-ish newtons. Now I'm going to move over here. So when I want to focus on this, I know that since the leftward component of this is 53.85 newtons, the rightward component is also 53.85 newtons. If this has a mass of 4 kilograms, I know that the downward force is going to be 39.2 newtons because that's the weight of this object. And therefore the upward component on this also has to be 39.2 newtons. So if I want to find T3, it's got to have a horizontal component of 53.85-ish, a vertical component of 39.2-ish. So that means the tension there is the Pythagorean resultant of that, so it's around 66.6 newtons. And the angle in here is inverse tangent of 39.2 over 53.85. So that's a 36-degree angle. So that was kind of a nice one. Lots of little steps, but hopefully you see the connections between the steps. Problem 30 is about a forehead withstanding a blow. I think I put a picture for that on there. And so on your syllabus, that is. So it can withstand a force of 6,000 newtons. The cheekbone can only withstand 1,300 newtons. So it says 140-gram baseball, 0.140 kilograms, is moving 30 meters per second, strikes your head, and stops in 1.5 milliseconds. So that's 0.0015 seconds. And so first, find the acceleration of the ball. Change in velocity over change in time, so that's a magnitude of 20,000 meters per second squared. So to find the force, if I've got a mass of 0.14 and the acceleration I found earlier, that's 2,800 newtons of force of the ball on the face or face on the ball. So A and B for that are going to be equal to each other, interactive forces. And so then if that hits the head, you're going to be fine because it's less than 6,000 newtons, which is the force necessary to crack your skull. If it hits your cheek, it's a problem because it's more than 1,300 newtons, which is required to refracture your cheek. Pretty cheeky. The last three here for Chapter 7, I'm probably going to do this last one which was a challenge problem in the room because I think it's a really interesting problem. This one's pretty cool. It's a Federation starship and a shuttlecraft. They have different masses. So the starship's 100 times more massive than the shuttle, and it's supposed to have a tractor beam, and the tractor beam can exert 40,000 newtons. And so you want to find the acceleration of each ship. Your goal is essentially to figure out how far the starship moves. Well, you could do that by saying, oh, it's 0.02 meters per second squared, and then you need to figure out how much time that's accelerating for. Well, if they're going 10,000 meters in the relative motion, they're approaching each other with a total of 2.02 meters per second squared of acceleration, because the shuttlecraft is accelerating at this rate, the starship's accelerating at this rate, then I can use this formula to figure out the time. So if you didn't take I mean, this 0.02 into account, your answer would be slightly off. So I get that it's going to be 99.5 seconds before they would collide, and in that 99.5 seconds, I'm going to use this again, and now the Starship is only moving 99 meters. So of the 10,000 meters, basically 9,901 meters is moved by the shuttlecraft, 99 meters is moved by the Starship. Makes sense. 100 times the mass, 1/100th about of the change in position. So for number 45, you have an object. This is called a bosun's chair. And the person is sitting in the chair, the rope is connected to the chair, and the person's pulling on the rope, and they want to accelerate themselves upward. So the total mass of the system is 70 kilograms for the person, 10 kilograms for the chair, so that's 80 kilograms. They want to accelerate up at 2 meters per second squared. So the net force is going to be m system times acceleration. That's this, 80 times 0.2. What forces are causing that? Well, if I do my free body diagram here, if there's two ropes pulling up, they each have a tension, gravity is acting down. So I have tension of both ropes. I assume they're going to be equal since they're both vertical. Minus mg is equal to mass times that acceleration. So 2t minus 80 kilograms times 9.8 equals 80 kilograms times 0.2. So I get around 400 newtons of tension in each rope, 800 total newtons net force upwards. Or pardon me, not net force upwards. Net force upwards of 16 newtons. Again, if you used G is equal to 10 meters per second squared or 10 newtons per kilogram, your answer would be slightly different. Oh, I didn't get number 53 on here. Well, we will go over that in class, but I'll have to make sure that I get that. Sorry, I will stop that right now. I'd forgotten to scan it, so I'm not sure if I can do this and combine it to one video or not. But basically, you've got a 1 kilogram block on a 2 kilogram block. They're connected to each other. There's a coefficient of friction of 0.3 between the blocks and a coefficient of friction of 0.3 between the bottom block and the ground. It's pulled with a net force of 20 newtons. So there's lots of friction forces opposing things. There's a friction force here opposing the motion of this moving to the right. There's a friction force here between these two blocks that acts against the 1 kilogram block, trying to prevent it from going to the left. The friction between these two also acts as a member of an interactive force pair on the 2 kilogram block from the 1 kilogram block to try to prevent it from going to the right. So there's really 3 friction forces, 2 of which are here. So the friction force of the ground on the 2 kilogram block is mu times F normal. Well, it's 3 kilograms times 9.8 newtons per kilogram times 0.3, so that's 8.82 newtons. The friction force between these two is equal to the normal force caused by this block, which is 1 times 9.8, or 9.8 newtons, times 0.3, so that's 2.94 newtons. But that's also an interactive force pair with friction on this block, so there's 2.94 newtons of friction opposing its motion as well. So I have this as my master physics equation, but it's the applied force minus friction of the ground on the 2.0, minus friction of the 1.0 on the 2.0, minus friction of the 2.0 on the 1.0. So that equals the net force, which is 5.3 newtons, and then all over the total mass, which is 3 kilograms. So that is a really good challenge problem.